Welcome to the second video in this video series on atomic spectra. So first up, we're going to go through the solutions to the homework that I assigned to you in the previous video. So determine the energy of the photon, the frequency of the associated electromagnetic radiation, and the wavelength in nanometers produced when an electron makes the following transitions in a hydrogen atom: from energy level 5 to energy level 3, from energy level 5 to energy level 2, and energy level 5 to energy level 1. So in the first transition we're going to look at, from energy level 5 to energy level 3, we are going to look at this transition here, from where the electron has an energy of 21 times 10 to the minus 19 joules, and then it falls down to 19,4 times 10 to the minus 19 joules. So the energy of the photon is equal to the magnitude of the drop in energy of the electron moving from energy level 5 to energy level 3, which is this transition here. So the magnitude is represented with the absolute value lines, and E final minus E initial gives us the drop in the energy of the electron. The final energy is energy level 3 minus the initial energy, which is energy level 5. So that's going to be 19,4 times 10 to the minus 19 joules minus 21,0 times 10 to the minus 19 joules, which gives us 1,6 times 10 to the minus 19 joules, because we ignore the minus sign. Now this is in actual fact equivalent to 1 electron volt. Now looking at the frequency, we see that in actual fact that this is in the infrared range, because we're finding that it's falling from there to there, which is going to give us infrared. So we want to find the frequency of the infrared radiation, so we use Planck's equation for the energy of a photon. The energy of the photon equals h, Planck's constant, times the frequency of the electromagnetic radiation. We substitute 1,6 times 10 to the minus 19 joules for the energy of the photon, and then we equal it to 6,63 times 10 to the minus 34 joules seconds. That's Planck's constant. Don't worry, you don't need to know that off by heart. You can get that off the formula sheet that is always supplied to you in tests and examinations, times the frequency of the electromagnetic radiation, and then we divide both sides by Planck's constant, and we get 2,41 times 10 to the 14 hertz. Now you were asked to convert this to terahertz. Now terahertz is 10 to the 12 hertz, so that means we need to move the comma or the decimal 2 places to the right, which is the same as timesing by 10 to the 2, which means we need to divide by 10 to the 2 here, or times by 10 to the minus 2, which gives us the 10 to the 12, which is what we want because that's terahertz. So the answer for the frequency of the infrared radiation that is given off by the drop from energy level 5 to energy level 3 is 241 terahertz. Now using the classical wave equation, where the speed, in this case the speed of electromagnetic radiation, which we represent with c, is equal to frequency times wavelength. We want the associated wavelength of the radiation given off. C is 3 times 10 to the 8 meters per second. You also get that off the formula sheet. And this equals 2,41 times 10 to the 14 hertz. We don't use the terahertz, we use the 2,41 times 10 to the 14 hertz. We could have also used that. We divide both sides by it, and we get that the wavelength, lambda, is 1,24 times 10 to the minus 6 meters. Now, you were asked to write this in nanometers. So what we need to do, nanometers is 10 to the minus 9. So to go from 10 to the minus 6 to 10 to the minus 9, we need to multiply by 10 to the minus 3, which is like dividing by 10 to the 3. So if we're going to multiply by 10 to the minus 3, then we need to multiply this by 10 to the 3, which is the equivalent of timesing by 1,000. So the comma is going to move 1, 2, 3 places. 10 to the minus 9 meters is a nanometer. So this wavelength is equivalent to 1,240 nanometers. In the B question, we are looking at the transition from energy level 5 to energy level 2. So if we look here on the diagram, in the first problem we were going from energy level 5 to energy level 3. Now we are going to go from energy level 5 to energy level 2, and we can see that that's a bigger drop, so the photon should have more energy. And using the same method as we used previously, but just with different values, we now work out the energy of the photon to be 4,7 times 10 to the minus 19 joules, which is the equivalent of 2,94 electron volts, which is a higher energy photon than the one that's produced by the drop from energy level 5 to 3, which was 1 electron volt. So we can see that this falls in line with what we predicted. Note that for the final energy of the electron, we used energy level 2, which has a energy value of 16,3 times 10 to the minus 19 joules. So using that, we got that value of 4,7 times 10 to the minus 19 joules. Substituting that into Planck's equation for the energy of a photon and dividing by 6,63 times 10 to the minus 34 on both sides, we get that the frequency of the electromagnetic radiation associated with the photon given off is 7,09 times 10 to the 14 hertz. Note that this transition falls within visible light. If we convert this now to terahertz, we are going to move the comma 2 places to the right, which means that we're going to have to multiply by 10 to the minus 2 here, and that's going to give us the equivalent of 709 times 10 to the 12 hertz, which is what we want because that is terahertz. So it's 709 terahertz. And previously I mentioned that visible light is to be found in the range of several hundred terahertz. So that falls in line with that. We then substitute the frequency of the light into the general, or should I say the classical wave equation. So frequency is 7,09 times 10 to the 14 hertz. C is 3 times 10 to the 8 meters per second. We divide both sides by this value, and we get that the wavelength of light is 4,23 times 10 to the minus 7 meters. Now we want it in nanometers. So what we want is the wavelength to be in the form of 10 to the minus 9 meters. So that means we are making this factor 100 times smaller, which means we must make this number here 100 times bigger. So we move the comma 2 places to the right. So this becomes 423 times 10 to the minus 9 meters, which is 423 nanometers, which also falls into a well-known range for visible light, which is between 390 and 780 nanometers. So it's always good to look at the answers that you get and to relate them to what is practical and what you know. So in C, we now look at the transition between energy level 5 and energy level 1. So we're looking at this transition here of an electron falling from there all the way down to the ground state, energy level 1, which we have defined as a 0 joule ground state. So that's the zero potential. So we can see here there's going to be a much bigger drop in energy in the electron. So the energy of the photon must be much bigger than what we previously worked out when we worked out the energies of the photons produced by the drop between 5 and 3 and 5 and 2. So now working out the energy of the photon produced by looking at the drop-in energy of the electron, but now we use the ground state, energy level 1's energy, which we've defined as the lowest energy, 0 joules. So the final energy is energy level 1. So it's dropping from 21.0 times 10 to the minus 19 joules. Therefore, the energy of the photon is 21 times 10 to the minus 19 joules, which if we divide by 1.6 times 10 to the minus 19 joules per electron volt, we get 13,13 electron volts. So we can see that the energy drop is much more, therefore the energy of the photon produced should be much higher. And it is, because it is 13,13 electron volts in comparison to the 2,94 electron volts for the transition between energy level 5 and energy level 2, which is greater than the energy of the photon that is produced by the drop of the electron from energy level 5 to energy level 3. So we can see our values fall in line with what we can see on this diagram. Substituting 21 times 10 to the minus 19 joules into this equation and solving for the frequency of the electromagnetic radiation, which we know is going to be ultraviolet light because it's falling into this series here of transitions, then we find that the frequency of UV is 3,17 times 10 to the 15 hertz. Now if we are asked, which we were, to convert that to terahertz, then that means that we want to write the frequency as in the form of times 10 to the 12 hertz. Now that means that here we need to reduce this by 10 to the 3. So we do that by dividing by 10 to the 3 or timesing by 10 to the minus 3. But that means that we've got to multiply here by 10 to the 3, which is the same as moving the comma 3 places to the right. So this is equivalent to 3,170 times 10 to the 12 hertz, or 3,170 terahertz. And for UV, we find that the frequencies are much higher. They are not in the hundreds of terahertz, but rather in the thousands of terahertz, as we can see here. Now we substitute this frequency of UV into this familiar formula for the wave equation, and using C for electromagnetic radiation, we get that the wavelength of UV is 9,47 times 10 to the minus 8 meters. If we want to convert it to nanometers, which we were asked to do, then that means we want to write it in the form of 10 to the minus 9 meters, which means that we need to multiply by 10 to the minus 1 here, which is the same as dividing by 10 to the 1. So if we're going to do that, we're going to times by 10 to the minus 1 here. It means we've got to balance it by timesing by 10 to the 1 here, which is the same as moving the comma 1 place to the right. So we get that this is equivalent to 94,7 times 10 to the minus 9 meters, which is the same as writing 94.7 nanometers. So to revise, let's look at the transitions and the series of transitions that we've looked at before. Now that we've done the calculations, we can see where these wavelength values come from, and note that as the electrons fall down from higher transitions to lower transitions, that the wavelength increases, which means that the frequency and the energy of the photons given off decreases, which makes sense. So if we are to take all the possible transitions that electrons can make, and let's say we have a population of hydrogen atoms in a gas discharge tube, That means we're going to have billions and trillions of these hydrogen atoms. Even though it would be at a low pressure, there still will be countless atoms. And as the gas is energized by the high voltage that is set or created across the gas discharge tube's electrodes, the collisions of the electrons which form the current going through the gas discharge tube, when they collide with the various atoms, will set the electron in each atom to rise to different energy levels. So in a population of hydrogen atoms, we'll get all the varieties of transitions that are possible. And so if we look at the full spectrum that would be produced by all these transitions, including seeing the unseen, being able to detect the transitions that give off photons that are in the ultraviolet range and outside of the visible range, for instance in the infrared range, then we get a whole series of lines. So the Lyman series, as we've worked with before, is where electrons, energized electrons, fall back to the ground state, giving off high energy photons. So that would be the Lyman series. Then the Balmer series is where energized electrons fall down to energy level 2. That gives off visible light, and we would see that would be in that range there. The Paschen series is where infrared radiation is produced with electrons falling down to energy level 3. But then we get other series as well, Brackett and Pfund series. So we see here now a full or a more extensive spectrum of hydrogen. Now, please just note that these lines are being represented here with a logarithmic scale. So if one were to actually plot this according to where you would actually find these bands, they would be a lot further apart. But this gives you an idea of the huge variety of photons that are given off in the simplest of all atoms, the hydrogen atom, which has just one electron. Now, one of the amazing things about atomic spectra is that every single element has a unique line emission spectrum. And the reason for that is that every element has got a certain amount of protons in the nucleus and a certain amount of electrons in the energy levels. And because of the force of attraction between these, where the energy levels are to be found varies from atom to atom. And so when electrons make transitions, and especially with multi-electron atoms like lithium and sodium and potassium, which are way more complicated than hydrogen, then we find that we get many, many more photons being produced than what we saw in hydrogen, because there are more possibilities with more electrons. And so these spectral fingerprints enable us to identify what the source of the electromagnetic radiation is that gives off EMR, say for instance in a star. So this is a very, very useful means to identify elements in astronomical objects, because every element's atoms, when excited, have unique spectral fingerprints. And as you will see a little later on in this video, this opens up the universe to us so that we can and have been able to learn so much about the universe that we would never have been able to know about and to discover if it wasn't for the use of atomic spectra and molecular spectra in astronomy. So when an incandescent light source gives off electromagnetic radiation and that electromagnetic radiation is dispersed or split up into its individual frequencies, either by means of a prism or by means of a diffraction grating, then we get a continuous spectrum. We've spoken about this before. If we take an element and we heat it up so that it's a hot gas, and then so that it gives off electromagnetic radiation, and then we split up that electromagnetic radiation, we do not get a continuous spectrum, but rather what we get are bright lines, what we call bright line spectrum or line emission spectrum, which we have spent quite a bit of time on. But now, if we take an incandescent light source and we pass it through a cold version of the same gas, then what we find is we get the inverse. So we have in the background, we have the continuum spectrum, the continuous spectrum of the incandescent light source. But where these bright lines occur, we now find that the light is missing. And so what's happening here is that photons are being absorbed by the atom, and they are putting electrons from lower energy states to higher energy states. And I encourage you to look at the associated video that is with this video to get a deeper understanding and explanation of how that works. But in essence, it's just the reverse process, where with emission line spectra, the excited electrons fall down and give off photons. What happens here is the gas, because it's cold, the atoms are in a low energy state, and what happens is when the light goes through, the frequencies of light in the continuous spectrum that match transitions between energy levels in the atoms of the cold gas are then taken into the atom, and they are absorbed by the atom's electrons, pushing the electrons up into a higher energy level. So it's energy conservation again. So those energies are missing because they have given energy to electrons to push them up into a higher energy state. But only certain bands are missing, which correspond to the energies of the energy transitions between energy levels for the electrons. So to revise, an atomic emission spectrum is formed when certain frequencies of electromagnetic radiation are emitted, and note, due to an atom's electrons making a transition from a high energy state to a low energy state. Whereas an atomic absorption spectrum is formed when certain frequencies of electromagnetic radiation that passes through a medium, example a cold gas, is absorbed. And so we can see where in a hydrogen emission spectrum, where you find the bands at the same wavelengths, in an absorption spectrum you'll find that there are dark bands because those frequencies of light are emitted. So this is beautiful proof. It's double proof of the specific or quantized energy levels of electrons in atoms. Have you ever wondered how astronomers can tell us that there are certain gases in certain stars and in certain galaxies? They've never gone there. They've never sent a probe there that has been able to collect samples. So how do they know? Well, the way they know is through spectra. And we are going to look at an example of the spectra from the closest star to us, namely the Sun. And albeit that this is not part of the syllabus, we would be doing you a huge injustice if we did not discuss Fraunhofer lines. Now, what are Fraunhofer lines? Well, Fraunhofer lines are the lines that one finds that are missing on the spectrum from the Sun's electromagnetic radiation. So when we look at a rainbow, we see red, orange, yellow, green, blue, indigo, violet. and it's easy to think that it is a continuous spectrum. But on closer inspection, a German physicist by the name of Joseph von Fraunhofer discovered that there was a pattern of dark lines in the sun's electromagnetic spectrum. And he was a really smart guy, and he worked out that in actual fact, these dark lines were actually absorption spectra. But not only the absorption spectra of one or two elements, but of a whole range of elements. Now, in a laboratory on Earth, we can produce absorption spectra for specific elements as a control or as a reference. So when one looks at the Fraunhofer lines, one can identify the line's wavelengths and then look at where on a standard absorption spectra you would find a line like that. So what they do is they decompose these lines, this resultant absorption spectrum, they decompose it into the absorption spectra of simpler substances, of atomic elements and of molecular compounds. And when they do that, they are able to give us a huge amount of information about the star. So for instance, the major Fraunhofer lines and the associated elements that they represent are shown in the following table, and we see there's a lot of oxygen, there's hydrogen, there's sodium, there's helium, there's mercury, there's iron, there's magnesium. And so these elements are to be found in the sun. And so as the electromagnetic radiation leaves the surface of the sun and passes through the atmosphere of the sun, which is very complex and has many different substances in it, the photons that correspond in energy to the transition of electrons of substances inside the sun's atmosphere that are at a lower temperature than the sun's surface will then go missing, because they will be absorbed by the electrons in these substances and will excite those electrons. But they will no longer continue with the rest of the photons in the electromagnetic spectrum that move through space toward the Earth. So they will be missing. They will have been absorbed. But it gets a bit more complicated than that, because now when that electromagnetic radiation enters the Earth's atmosphere, the Earth's atmosphere has substances like molecular oxygen, molecular nitrogen, it has hydrogen, and so the photons of electromagnetic radiation from the sun that correspond to the transitions of electrons within those substances will then excite those electrons, and those photons from the sun will also be missing. So by the time the electromagnetic radiation from the sun reaches the surface of the Earth, there has been a double absorption. And so we have all these hundreds of Fraunhofer lines that are in the electromagnetic spectrum from the sun's radiation. Now scientists are very clever, and they are able then to work out which of the lines represent absorption from the Earth's atmosphere and which of the lines represent absorption from the sun's atmosphere. So we can get a huge amount of information about the sun as well as the Earth's atmosphere from the absorption spectrum of the sun. How do we know that the universe is expanding? How do we know that the Big Bang Theory is actually true? Well, one of the ways of proving this is by looking at absorption spectra of galaxies. So galaxies are made up of huge amounts of gas. A lot of it is hydrogen, but also there are heavier gases like methane and carbon dioxide, but also a lot of dust. Now, when we look at a galaxy and we split the light up from that galaxy, we get spectra that look like this. So there is a continuous spectrum in the background, but then as that electromagnetic radiation passes through the dust and the gas in the galaxy, we find that these photons are missing. Now, these patterns, as we explained with Fraunhofer lines, they can be deciphered, deconstructed, so that we can see what substances absorbed photons in order to produce those patterns. But now there's something else that's really, really interesting. We also know, based on our experiments in labs, where these lines should appear, at what wavelengths, like we worked out earlier in the video, where these wavelengths would form, and they would correspond to specific photons that were missing, which corresponded to certain transitions within the atoms, the electrons in atoms. But what they found to be very, very interesting is when they actually worked out where these lines were forming in comparison to where they formed in a laboratory on Earth, they found that they were not forming in the same place. And there is a very deep reason why. So let's take a galaxy's electromagnetic spectrum. There's its absorption spectrum. Now, when we look at this galaxy, we find that the wavelengths have moved to the right of the spectrum. That the wavelengths have shifted to the red part of the spectrum. So they refer to this as a red shift. Now I want to refer you to the Doppler effect. We've already done acoustic Doppler with sound. So recall that when a source was moving toward an observer, the frequency of the perceived waves increased and the wavelength decreased. And when the source was moving away from the observer or the listener, then it seemed as if the wavelength was stretching and therefore the frequency dropped. We call that a Doppler shift. Now, because light has got wave-like properties, it too undergoes the Doppler effect, but not with sound waves, but with electromagnetic waves. Now, red light is lower energy light, which means it has a lower frequency than the blue, indigo and violet part of the spectrum. So if light wave were to stretch, then its wavelength would get bigger and its frequency would get less. So they observed this experimentally, and they had to interpret why this shift in the light coming from galaxies was taking place. And a scientist by the name of Edwin Hubble measured these shifts and worked out that the reason for these shifts was that the galaxies were moving away from the Earth. And so Edwin Hubble, he looked at many different galaxies in the universe and came to the conclusion that most galaxies are in actual fact moving away from each other. And this was quite surprising because up to that point, many of the great scientists, including Newton and Einstein, believed that the universe was actually static, that it wasn't expanding or contracting. And so the conclusion of Hubble was that in actual fact, the universe was expanding in all directions. He even set up a law that's known as Hubble's law, which states that the further a galaxy is, the faster it is moving away. And so this led to a whole new perspective of the universe, and this resulted in many astrophysicists and cosmologists devoting their whole professional lives to trying to explain why this happened and what would happen to the universe in the future if it was continually expanding. So this diagram here quickly illustrates the principle of the Big Bang. So you have a galaxy that gives off a spectrum of electromagnetic radiation, and the wavelengths travel toward the Earth. But now, over a period of time, as the universe expands, space expands, and so the wavelength starts to stretch. And the longer it takes for the light from the galaxy to reach the Earth, because of the fact that the galaxy is further away, it's in a part of space that is traveling faster because of the expansion, we find that the wavelength stretches even more. And so as the wavelength stretches, so it gets bigger, and so it moves closer to the red side of the electromagnetic spectrum. If a galaxy were to move closer to the Earth, then the Doppler shift would be a blue Doppler shift, where the wavelength would get shorter, and so it would then, the bands on the absorption spectrum would move toward the blue side of the spectrum. But for the most part, when we look at galaxies, most of them are actually moving away from the Earth because space is expanding. I would like to end off this video with a humorous story. It's a true story, and what it does is it shows us that, or illustrates that, science is not all perfect, and that sometimes mistakes happen that win scientists Nobel Prizes for physics. And so the story is about two scientists named Penzias and Wilson, and they were working at the Bell Laboratories in New Jersey in the United States of America. And what they were trying to do is they were trying to take this radio horn and use it to study the radio signals from the Milky Way galaxy in order to learn more about the structure of the Milky Way galaxy. But what they found is that they continually had interference. They had this noise, as they called it, that disturbed the signals that they were actually trying to study. And they were hugely irritated by it. And so they tried all sorts of things. They tried to take all the pop rivets that were on that particular radio horn and cover them with tape. They even went to the extent of removing the bird poo from the pigeons that were nesting inside the radio horn. And no matter what they did, they could not get rid of this background noise. A few kilometers down the road at Princeton, there were a group of theoretical physicists who had predicted that in the beginning of the universe, that the universe was exceptionally hot, and that as it expanded, it would cool down, and it would get to a point where it was cool enough in order for the electrons to combine with the nuclei and then to actually give off photons of electromagnetic radiation. So they predicted that at the beginnings of the universe actually gave off light at around about 380,000 years, and that this light was sort of a reddish-orange color. And they also predicted that as the universe expanded, if the Big Bang theory was true, that these wavelengths of visible light would then be stretched by the expansion of space, and they would be able to be determined, or should I say detected, in around about the microwave range. So after billions and billions of years, with the stretching of space as the universe expanded, the wavelengths would actually expand. But this was just a theoretical prediction. The strange thing is that these two gentlemen actually discovered the microwave radiation by mistake. The noise, the irritation, was in actual fact one of the greatest discoveries in the 20th century. They had discovered the afterglow of the birth of the universe, and they won the 1978 Nobel Prize for Physics. And guess what? The guys that actually had predicted it never won the Nobel Prize for Physics. So who says that physics is always fair? Today, mankind sends space-based telescopes like the Planck telescope into outer space in order to study what they call the cosmic microwave background radiation of the universe, and produce a map like this of the universe, which then gives us a huge amount of information, not only about how the universe is now, but how the universe actually formed at its very beginning. So we can see this discovery of atomic spectra, molecular spectra, emission and absorption spectra was certainly one of the greatest discoveries of mankind when it came to understanding electromagnetic radiation and its relationship to the internal structure of atoms and molecules.